Hey guys, I want to make a video on Bernoulli's equation. Bernoulli was a dude who figured out a lot about fluid flow, how fluids flow, what happens when they are flowing past certain objects, and it explains a lot of phenomena, and it's a big deal. So first I want to start off, this is a picture of him right here, and this is the equation. There it is. Now, the big irony here is that you've seen this before, you actually know what this is. You know a lot of these little symbols. So you know what this is, you know what that is, you know what this is, maybe, probably, right? But you're sitting there going, how did this come to be? What is this big mess of stuff? And I'm going to show you that you actually know what this is, right? So if you read up here, you see that in the absence of friction or other forces, other non-conservative forces, the total mechanical energy of a system remains constant. And it's that second part. The total mechanical energy of the system remains constant. Where have I heard that before? Roberts, where have I heard that before?
Conservation of energy.
Oh my God, you're right. It's the conservation of energy. Holy cow. This is conservation? We did this last year. So here's where we start. Last year we said that the energy before is equal to the energy after. And then we talked about what are all the different types, right? And we said we can have potential, we can have kinetic, we can have what's called elastic, and then we can do work. We had a bunch of problems where we had things going up and down hills and they were going through wind tunnels and we were calculating things. The work on this side was the work that's helpful, that adds to the overall system, and this work on this side is the work that takes away, and that's usually the work done by friction. Now, if we put all of our equations, remember that work is FD cosine theta, but we're not going to worry about it. Theta here is going to be 0. So it's FD. PE is mgh, K is 1/2 mv squared. EPE was elastic, where we have springs, and that's 1/2 kx squared. Before and after. And remember that it can change. So you might have potential and elastic before something happens, and then it might turn into kinetic after, something like this. Bernoulli's equation, if I go backwards, is just a statement of that conservation law. So I'm just going to show you how we get to here. Okay. Once again, this P is pressure. This is density. This is velocity. This is height. So you kind of see where that's coming from. This looks a lot like mgh, right? This 1/2 rho v squared looks a lot like 1/2 mv squared. Okay? So how do we get there? Well, we start with this, right? Okay, so here's our equation, right, guys? Now, the first thing that we're going to take out of here, obviously, is this. We're taking this out. And we're going to take it out on both sides. And why are we doing that? Why are we getting rid of elastic potential? Because we're talking about fluids. And springs don't really come into play here. So that goes away. Isn't that nice? All right, now, next thing we're going to do, we have to make a leap here, right? We need to get this to look like this. We need some rows here. We need density in there. Density, velocity, we already have. And we need P's, that's pressure. So how do we do this? What kind of fluid is this? All of our fluids are going to be these perfect fluids. We're in physics land, and they are incompressible. So if you have a fluid that's incompressible, that means whatever comes in the system is going to go out. Right? We talked about when you put your thumb over the hose and how the speed has to increase. Right? It's kind of the same deal. Well, it's the same deal here. So let's make this leap. Okay. If the fluid is incompressible, then something is going to be constant all the time, right? You have an amount of fluid in, same amount goes out, so what is going to be constant? Boom, volume. Volume is constant, because whatever goes in must come out, so the same volume of stuff. And so what we can say is that volume is the same on both sides, and we can divide by volume. And guess what? I can divide or multiply by whatever I want as long as I do it to both sides of my equation. You can do whatever you want as long as you do the same thing to both sides. Here's my equal sign right there. So I divided everything by volume. So what happens when you divide by volume? What happens when you take mass and divide by volume? What do you get? Mass divided by volume is density. This becomes rho g h. This becomes 1/2 rho v squared. Okay? And this is how we arrive at an equation that looks crazy like this. This is now 1/2 rho v squared was 1/2 mv squared, and rho gh was mgh. Yes? Okay. And then pressure. What about pressure? So, if you can follow this, I'm writing with my mouse, which is a little tricky. So we took FD and divided by volume, right? Now, I'm going to look at this in another way to make it go faster. I hope it goes faster. What is the unit for force? It's Newton. What's the unit for displacement? It's a meter. What's the unit for volume? It's meters cubed, right? Volume is length times width times height, which is meter times meter times meter. So I have newtons times meters divided by meters cubed. This meter up here cancels out one of these three down here. So this one up here cancels one of these three, and you get newtons per meter squared as your final unit. What is the unit for Newton represent? It's a force, right? Meter squared is the unit for area. And what is force divided by area? It's pressure. So this is how we get this full equation. Okay. Okay. So the principle uses this equation. This equation is really just conservation. Now, this equation is used to discuss what is called Bernoulli's principle, which states that the total pressure of fluid flowing in any type of system that is enclosed is going to be constant. Okay. Bernoulli's principle also states some pretty cool things, like if you have a faster moving fluid, the pressure in the faster moving fluid is going to be less than the slower moving fluid. And this is some pretty neat stuff. Some of the demos I do in class is I'll take a piece of paper and I will put it up to my mouth and I'll blow over the top of it. And what happens is that the paper comes up. It's pretty neat. Right? See how it flaps up? That's because the air moving fast on the top has lower pressure than the air on the bottom, and so it goes up like this. And there's a lot of other neat little things that happen when we're talking about something like this. So what's cool about this is that we can use this to talk about conservation within a fluid flowing through some system like a pipe, right? So all of the energies you have before is equal to all of the energies you have after, which means the sum of the pressures and the fluid levels and the heights are all the same before versus after. Excuse me. Okay. Another way to say it is that this side here is equal to some constant. This is a thing. Okay. And we can use this when we do problems. So one common example, I don't know if it's common, but an example is where you have some sort of reservoir and you have a fluid, maybe it's water, and you have a hole near the bottom or somewhere on the side, preferably nearer the bottom than I got here, and you take something out and water starts coming out, right? So you have some reservoir and then you take a little spigot out and water starts coming out, right? And this is a very classic problem, and what they're going to say is, well, can you find the speed of the water as it's coming out, right? And so we're going to use Bernoulli's in order to solve this. Okay, now we're going to cheat just a little bit in order for this to work. Okay, so the first thing we're going to say is we're going to say that the pressure up here, this has to be open. Okay. So that there is air pressure, right? We're going to say that the pressure here is going to be the same as the pressure here. Now, is that true? Technically, no, but there's not a big enough difference in height for us to really tell. And if you could actually measure that, it's not going to be a big difference. So the pressure here is going to be the same as the pressure at this little hole here. What is that pressure? It's atmospheric. So the pressures will be the same. Okay. We're going to cheat again, and we're going to say that when you let the water go and it starts flying out here, right, the velocity that this level of water starts moving down is going to be 0. We're cheating. What happens is that this is a very small hole in relative to this part here. And so what happens is when this water starts squirting out, this big open part, it just barely starts to move down. Just barely. You can hardly even tell. So we're going to cheat. We're going to say that this portion right here is going to move with a speed of 0. And so we're going to solve for this speed right here, which we would call V2. So we're going to invoke Bernoulli's equation. We're going to say that the pressures are constant, so the P's go away. Okay. And we're going to say that the initial speed of the top of the water is going to be 0. So when we let this water start flying out, this just barely starts moving down. Okay. And that gets rid of these two things, and that gets rid of this sucker. So we have left, rho GH on the left, right? Because this water is at some height. Okay. There's a height difference here, right? And the top of the water is at a height above the ground. Water is flowing here, so that's the 1/2 rho v squared right here. V2 is what we're going to solve for. And then rho GH is whatever that height is here. Okay. And when we do the mathematics, right, you get V2 is going to be equal to square root of 2g delta H. This is H2 minus H1. This looks very similar to something else that we did not too long ago. If you recall, there was a video from last week, and you had to calculate speed of this roller coaster car at its lowest point. And we did the same thing there. Right? We use conservation, mgh equals 1/2 mv squared, and we got this right here, which was v is equal to the square root of 2gh, which is pretty cool. Okay? Because we're doing the same thing here. Here it has a cool name. It's called Torricelli's theorem. So you can go home and tell people. Well, you can be at home and just tell people. We're learning Torricelli's theorem, right? It's really the same process, but what we're doing is we're using fluids, okay, instead of like something going from up here to down. But that's what's going on here, is that we have water at the top, and where is it going? It's going to go down, right? It's going to come out of here. So the water at the top has potential, and that potential turns into kinetic, right? There is a change in height here because it isn't right on the ground, so you have an H2 and you have an H1, and there you go. Here's another case where you have some enclosed system. The height, there is no height change, right? But you have a cross-sectional area change, right? So you have a low speed here and a higher speed there, right? Which means you have higher pressure here and lower pressure there, okay? But because there's no height change, this goes away. And so you're left with this right here. So you might see something like this. And so what's going to happen is you're going to have to calculate for something. They may tell you the pressure in this little region here, and you have to calculate pressure in that part, something like this. And they're going to give you all the other stuff. Okay, so here's a problem that puts it all together. Let's take a little look. Can you solve this? Look at the picture. What kind of problem do you think this is? If you read the problem, they're asking, what volume of water will escape per minute? A volume per minute. What is that? That's flow rate. But this looks like a Torricelli's problem. So what it does, it puts it all together. So I want you to give it a shot. Yep, give it a shot. It is Bernoulli and flow rate. Can you try it?